Greetings, ladies and gentlemen. Welcome to the portal. It is your teacher here, Mr. Sehla. Okay, guys. So today's video is going to focus on titrations. Most importantly, it will focus on the calculation part. I've done other videos whereby they focused on the theory part of titrations. Okay, so now, without wasting any time, let's start. Okay, so you will remember from previous videos that we defined titration as a method of determining the concentration of a known substance using a standard solution. Okay, so in order for you to understand this definition, you have to know what is a standard solution. Okay, so we defined standard solution as a solution with a known concentration. Okay, that was our definition of standard solution. Also, I also introduced terms like a titrant and the analyte. So the titrant, it is our standard solution. We pour the titrant into the burette, okay, and then the solution with the unknown concentration, the one we don't know its concentration, we transfer it into a conical flask or Erlenmeyer flask, okay, and then we add some indicator in there, and then we perform our titrations. Okay, so now during our titration, there is a point we call equivalence point. Okay, so equivalence point, it is a point of a titration where the moles of the acid have completely reacted with the moles of the base. Okay, so at the equivalence point, as you can see, equivalence means equal, you see. So at that point, the moles of the acid are equal to the moles of the base. Okay, I will show you what I mean by that, because it can cause quite a confusion. So but equivalence point, you cannot see it with your own eyes. Okay, so we can only see the end point, because the end point, it is a point of a titration where the indicator changes color. Okay, so yeah, and the end point is just few milliliters away from the equivalence point, maybe 0.0 something or 0.1 or 0.2 milliliters away from equivalence point. Okay, so now I want to talk about the at equivalence point. Okay, at equivalence point, the amount of the hydronium, right, it is equals to the amount of the hydroxide at equivalence point. Okay, this is what it means when they say moles of acid equals to moles of base. We know that our acid, we know we are talking about the hydronium, and our base, we're talking about the hydroxide. Okay, so, and now when we are talking about a specific acid like sulfuric acid being titrated with sodium hydroxide, it does not necessarily mean that 1 mole of sodium hydroxide is equals to 1 mole of sulfuric acid at equivalence point. No, it doesn't mean that. When it says moles of acid are equals to moles of base, it just simply means the mole of hydronium is equals to the mole of hydroxide. Okay, so we can do an example on that. Okay, so if now I have 1 mole of hydronium in solution, and then I have 1 mole of hydroxide in solution, right? Remember, acid and basis reactions are neutralization reactions, right? So I'm expecting a neutralization here. Okay, so what is going to happen? So here, if you can check, I have a proton donor, which is the hydronium, and I have a proton acceptor, which is the hydroxide. So this hydronium is going to donate a proton to hydroxide. Then the hydroxide is going to form water. So when this hydronium donates the proton, it will be H2O, right? So now plus when hydroxide accept the proton, it will be what? H2O as well. You see, so now H2O is neutral and H2O is neutral. You see, so what do I have? So I can see that when I have 1 mole of acid and 1 mole of base, I end up with what? I end up with something that is neutral, which is water. So I can conclude that when the number of moles of acid are equal to the number of moles of base, I have what? Neutralization. So this is the end of my titration. Okay, so this is the end of my titration, but we cannot see equivalence point with our own eyes. So we always end our titration with a little bit extra of either maybe the acid or the base. Okay, so but at the equivalence point, this is what is happening. Okay guys, so let's say now we have an example. I have an acid and a base. Okay, let's say now I have a reaction whereby I have 1:1 reaction of acid and base. Okay, so let's say we have hydrochloric acid titrated with sodium hydroxide. Okay, so giving us what? Giving us sodium chloride plus water. Okay, so here we can see that, oh, we have 1:1 stoichiometric relationship, right? Because the equation is balanced, and we can see that in front of the HCl and in front of the sodium hydroxide, the stoichiometric coefficients, they are 1 and 1. You see, so now what happens now? Because this one it is our acid, and this one it is our base. Okay, so now if before I mix the HCl and the sodium hydroxide, remember that they are in solutions, they are in aqueous solutions, meaning that they are in solutions that contains water. Okay, so now HCl in water, what does it give us? It gives us hydronium plus what? Plus chloride ion. Okay, what about sodium hydroxide in water? Sodium hydroxide in water, sodium hydroxide does not react with water. Okay, so there is no ionization or dissociation. There's no ionization of water, there's only dissociation of sodium hydroxide, and dissociation looks something like this: Na plus plus OH minus. Okay, so now you will notice that for my acid in solution, I have 1 mole of hydronium, and for my sodium hydroxide, I have 1 mole of hydroxide. So meaning when my ratio is 1:1 of the HCl and the sodium hydroxide, also the ratio of the hydronium ion and the hydroxide ion is 1:1. Okay, so now but if I have for example sulfuric acid plus for example, let's say potassium hydroxide. Okay, what am I going to have? I'm going to have 2 molecules of water plus potassium sulfate. Okay, so now you will notice that 1 mole for 1 mole of H2SO4, I need 2 moles of potassium hydroxide. So now at the equivalence point, in order for me to have a complete reaction between the acid and the base, I need 1 mole of sulfuric acid and 2 moles of KOH, right? Now you'll notice that this seems like I'm contradicting what I was saying about moles of acid equals to moles of base, okay? So that's why I said I don't want to say moles of acid equals to moles of base. I want to say the moles of hydronium equal to the moles of hydroxide. What did I mean by that? Okay, let me do this. So now, if I can say this sulfuric acid solution, this sulfuric acid in water, what does it give me? It gives me 2 moles of hydronium plus the sulfate ion, isn't it? Okay, and what about the KOH? So KOH, if I have 2 KOH, right? 2 KOH is going to give me 2 K plus plus 2 OH minus. You see, when I say at the equivalence point, the moles of the hydronium are equal to the moles of hydroxide. This is what I mean. Notice this. This is 2 moles of hydronium. This is 2 moles of hydroxide. You see? So now, even though here, when I'm talking about the acid itself and the base itself, the stoichiometry is 1:2. But when I talk about the hydronium and the hydroxide, it's 2:2. You see? So at the equivalence point, the moles of the hydronium are equal to the moles of hydroxide. Okay, so now let's get into it. Okay, so now let's say I have the same HCl plus sodium hydroxide, okay, giving us water plus sodium chloride, right? Okay, so because here I have my acid and I have my base. Now and I have the stoichiometric coefficients, which is 1 here, which is 2 here, which is 1 and 1. Okay, sorry, 1 and 1. Okay, so now in notation I can write this 1 n for moles. 1 mole of HCl requires 1 mole of sodium hydroxide to reach equivalence point. You see? So now when I'm going to do my calculations, I'm going to use this ratio. Okay, so depending on what they have given me, if they give me the hydrochloric acid as my standard solution and then this as my analyte, so first things first, I have to calculate the moles of the standard solution and then use the stoichiometric ratio to know the moles of sodium hydroxide. After that, use the volume of the sodium hydroxide and the moles of sodium hydroxide to calculate the concentration of sodium hydroxide. Okay, so I have an example that I was taken from a Siavula textbook. Okay, so you can access that by yourself. I will link it in the description. Okay, guys. So here's the question. We have a question. It is an example. So now it says given the equation. Okay, so there they've given us the equation. So it is sodium hydroxide plus hydrochloric acid plus sodium chloride and water. Okay, so before you can do anything, you have to check if your equation is balanced. Okay, so how do we check if it is balanced? We have to count the mass, both sides, both left and both right hand side. Okay, so Also, we have to consider charge. Charge must be the same on the left and on the right. Okay, guys. So now we can go on with the statement. 25 cubic centimeters of sodium hydroxide solution was pipetted into a conical flask and titrated with 0.2 mole per dm cube of hydrochloric acid. Okay, so what are we given? We are given that 25 cubic centimeters of sodium hydroxide. So they've given us the volume of sodium hydroxide. Okay, let's write it here. We are given 25 cubic centimeters of volume of sodium hydroxide. Okay, what else are we given? We are given that and titrated with 0.2 mole per dm cubed of hydrochloric acid. Okay, so using suitable indicator, it was found out that 15 cubic centimeters of acid was needed to neutralize the base. Okay, so calculate the concentration of the sodium hydroxide. Okay, so now the other information that they've given us is 0.2 mole per decimeter cube of HCl. Okay, what else did they give us? They gave us the volume, that the volume is 15 cubic centimeters of what? Of HCl. Okay, so now by definition, the solution with known concentration, it's called what? It's called a standard solution. Okay, so meaning now this is our standard solution, right? So HCl is our standard solution, and what we call our titrant. So and then this is our analyte. So what is it that we don't know here? We don't know the concentration of sodium hydroxide. Okay, so we don't know concentration of sodium hydroxide. So it's what we are going to determine. So we are going to determine this concentration of sodium hydroxide by performing a titration using the standard solution. Okay, so now how am I going to do that? Let me give you steps, right? So now you will notice that here I have stoichiometric ratios, right? Okay, so now step 1, what are you going to do? You're going to calculate the number of moles of the standard solution. Calculate the moles of standard solution. Okay, that's what we're going to do first. That's step number 1. So what do we have here? So we have the concentration and we have volume of the standard solution. Okay, so now you will notice that the volume is given in cubic centimeters and we want it in what? In decimeter cube. Why? Because our concentration, it has decimeter cube on it, you see. So what am I going to do? I'm going to take volume 15 cubic centimeters, okay, divided by 1000 cubic centimeters multiplied by 1 decimeter cube. Okay, so now here I can see that cubic centimeter will cancel cubic centimeter, and then 15 divided by 1000, I'm getting 0.015 decimeter cube, you see. So now my volume, it has the desirable units, the one that I want. Okay, so now let me calculate my concentration. So we know that concentration, I'm going to calculate my moles. Okay, we know that concentration is N over V, right? This formula, it is there in your formula sheet, right? But I want to calculate number of moles. So number of moles, I have to make N subject of the formula, and then now N is equals to CV, isn't it? So N is equals to concentration multiplied by volume. Okay, so now to be specific, I want to calculate the number of moles of the acid. Remember, I want to calculate my standard solution, and what is my standard solution in this instant? It is the HCl. Okay, so this HCl, it is an acid, so I'm going to say Na for number of moles of the acid is equals to Ca for concentration of the acid multiplied by Va, which is the volume of the acid. Okay, so now Ca, it is the concentration that we were given, which is 0,2 moles per decimeter cube. Okay, so multiplied by the volume that we just converted, 0,015 decimeter cube. Okay, you will notice that per decimeter cube cancel decimeter cube, you see. So when we multiply powers of the same base, we add the exponents. It means it is -3 plus 3, which is a dm exponent 0, and then any number exponent 0, it is 1. So we are left with mole. Okay, so I'm going to go on and say 0,2 multiplied by 0,015. What am I getting? I'm getting 0,003 moles. Okay, so which is the same as 3 times 10 to the power -3 moles. Okay, so this one is written in scientific notation. Okay, so what are the moles for? These are the moles for hydrochloric acid. Okay, so now we have the moles of hydrochloric acid. Now we need the moles of sodium hydroxide so that we can use the moles of sodium hydroxide and the volume of sodium hydroxide to calculate what? The concentration. Okay, so step 2. What do you do now? You calculate. Okay, let me do this. Use stoichiometry to calculate the moles of the analyte. Okay, so now we know that the ratio that we are given is 1 mole of HCl is to 1 mole of what? Sodium hydroxide. So this is the standard solution, this is the analyte. Okay, so we can see that this 1:1. Okay, so now meaning number of moles of the base, right, which is my analyte, sodium hydroxide, it is what? It is concentration of the base times volume of the base. Okay, but now I don't have the concentration. I can't calculate the number of moles. Okay, I only have the volume. So how am I going to calculate it? I'm going to use stoichiometric ratio. Okay, so now first of all, how much are the moles of HCl? So I have moles of HCl is 3 times 10 to the power -3. Okay, so now notice that this stoichiometric ratio, it's something like 1 mole of what? Of HCl is to 1 mole of sodium hydroxide, isn't it? Okay, Now I'm going to write the ratio there. So 1:1. Okay, so on the HCl I'm going to write what? 3 times 10 exponent -3, and then here I'm going to write x. Okay, so if I cross multiply, here I'm going to have 1 multiplied by x, which is x. Okay, and then 1 multiplied by 3 times 10 to the power -3, I'm going to have 1 multiplied by 3 times 10 to the power -3. So what is the answer? The answer is still the same. Okay, so now because I used my stoichiometry, it means now these are no longer the moles of sodium, these are no longer the moles of hydrochloric acid, but they are the moles of sodium hydroxide. Okay, now step 3, calculate the concentration of the analyte. How are you going to do that? From that formula we know that, oh, now concentration of the analyte, concentration of the base, is equals to number of moles of base divided by volume of base. Okay, so NB is what? 3 times 10 to the power -3 divided by volume of the base. We are given volume of the base is what? 25 cubic centimeters. Okay, so we are going to say 25, but 25, that 25 we have to divide it by 1000 so that it is in what? In decimeter cube. So 25 divided by 1000, we get 0.025 decimeter cubes. Okay, so 3 times 10 to the power -3 divided by 0.025, we are going to have 0.12 mole per decimeter cube. You see, we are going to have that. Okay guys, so this is the method that we used in stoichiometry in grade 11. Okay guys, so I will do the same problem but using a much simplified method, okay, that we use in grade 12. Okay guys, so now for the same question, right, notice to what I'm going to do. Okay, so now my stoichiometric ratio, please don't get confused, right? My stoichiometric ratios, right, this is the coefficient of acid and this is coefficient of base. Okay, so this time around the coefficient of acid I call it Na, right? So this Na, it is not the calculated number of moles of the HCl when I use this method, but it is the stoichiometric ratio of the acid. Okay, stoichiometric ratio, not ratio, stoichiometric coefficient of acid, right? And then this one is a base, NB, stoichiometric coefficient of base. Okay, so now because on what I was doing in the previous question, right, so in science we don't just use formula or equations that we don't know where they come from. Okay, so now stoichiometry is 1:1, right? And I say the stoichiometric ratio, coefficient of the HCl is Na and the coefficient of sodium hydroxide is Nb. Okay, so meaning that my relationship is Na is to Nb, isn't it? Okay, so because it's Na is to Nb, ratio it is the same as a division, okay? It's Na over Nb over Nb, isn't it? Okay, but we also know that N is equals to Cv, isn't it? And then now Na is equals to Ca/Va, isn't it? And then Nb it is equals to Cb/Vb. So it is actually what I was doing, but I just did it in longer steps. Okay, so now this is the stoichiometry. I've written the stoichiometry in terms of the concentration and the volume. You see, this is what it is now. So, and then now here on Na it is the coefficient, and Nb also coefficient. Okay, so I'm going to check the number here. So the number here is 1 and the number here is 1. So let me write my data again. So we were given 25 cubic centimeters of sodium hydroxide, and the volume of the base, which is the volumes of sodium hydroxide. Oh, that's the volume of sodium hydroxide. Okay, this is Vb. We were given Vb, and then the concentration of the base, which is the concentration of sodium hydroxide, it was not given. What else was given? We were given concentration of the acid, which is 0.2 mole per decimeter cube, right? What else were we given? We were given volume of the acid, which is 15 cubic centimeters. Okay, so now here I'm just going to take the values and substitute them here and solve for Ca solve for Cb, because this is what I'm looking for. Cb is what I'm looking for. So you can pause the video and calculate it. Okay, I bet you are done. Okay, let's get on with it. Okay, so now I'm using the formula. Okay, so I'm going to write it here. Na over Nb is equals to Kava. You see, Cb Vb. Okay, so Na, I'm going to look at the number in front of the acid. So what is the number in front of the acid when the equation is balanced? Is 1. Okay, so I'm going to put 1 over, what about Nb? Nb is also 1. Okay, so is equals to Ca is the concentration of the acid. Okay, it's 0.2. okay, multiplied by Va is the volume of the acid. Okay, so that volume divided by 1000 is what? Is 0.015 divided by Cb is what we are looking for, multiplied by Vb. So 25 divided by 1000, 0.025. Okay, so now you see we are left with Cb. You see, so now we can see that, oh, on the left we have 1 is equals to 0.2 multiplied by 0.015 is what? Is those moles. Is 3 times 10 exponent minus 3 divided by 0.025 Cb. Okay, so now if we cross multiply, we will end up with what? Cb, it is equals to 3 times 10 to the power minus 3 over 0.025. Okay, so now if you press your calculator, we can see that the answer is what? 0.12 mole per decimeter cube. Okay, So this is the same as what? This is the same as the one the other side. You see 0, 0,12. You see how many steps I have done here. Okay, so these are the conceptual steps. Okay, they test the concept that you as a learner, you understand the concept of stoichiometry and the concept of the mole. Okay, so you have to understand this kind of steps. Okay, and then the second one, this is just a plug and play. This is like pushing buttons. You are just pushing buttons. Something is there, you just substitute. But knowing this only does not necessarily mean you understand the work. Okay, so that is why I show you two methods, so that you guys can understand the work. I don't want you to cram the question papers. Okay guys, I want you to understand, to grasp the concept. Okay guys, so let's do another example. Okay, so now we have another example. They say 10 grams of sodium hydroxide is dissolved in. This one we're going to do it a little bit quicker with the formula only. Okay, 10 grams of sodium hydroxide is dissolved in 500 cubic centimeters of water. Okay, let's write the information. Okay, 10 grams, let's use the white. 10 grams of sodium hydroxide. Okay, it is dissolved in what? In 500 cubic centimeters of water. Okay, so what happened is this. So they added 10 grams of sodium hydroxide into a 500 cubic centimeter volumetric flask, and then they filled with water to the mark. Okay, so now using titration, it was found that 20 cubic centimeters of this solution was able to completely neutralize 10 cubic centimeters of sulfuric acid solution. Okay, so now what happened is that they took 20 cubic centimeters of this solution and they added it into something 20 cubic centimeters. Okay, actually, well, this is our standard solution, so they added this solution into a burette. Okay, and then now this solution was able to neutralize 10 cubic centimeters of acid solution. Okay, so now here 20 cubic centimeters of this solution of sodium hydroxide was able to neutralize 10 cubic centimeters of sulfuric acid. Okay, so now what do we have here? We have volume of sulfuric acid, we have volume of sodium hydroxide. We don't have the concentration of both, but here we can calculate the concentration of sodium hydroxide. Okay, let's do it quick guys. Okay, so now concentration of sodium hydroxide, we have M given mass, molar mass multiplied by volume. Okay, so what is our given mass? 10 grams over right, the molar mass of sodium hydroxide is what? Is 40 grams per mole. Okay, so multiplied by the volume. The volume is 500 cubic centimeters divided by 1000 is 0.5 decimeter cube. Okay, so what is our concentration? 10 divided by 40 multiplied by 0.5. okay, so the answer is 0.5 mole per decimeter cubed of sodium hydroxide. Okay, so now we have Cb, which is 0.5 mole per decimeter cubed. and then Ca is what we are looking for. We have Va, which is 10 cubic centimeters. We have Vb, which is 20 cubic centimeters. Okay, so now this is what sodium hydroxide plus sulfuric acid. Okay guys, so what are the products? The products are what? Sodium sulfate plus water. Okay, so but now balancing it, so for 1 mole of sulfuric acid we need 2 moles of sodium hydroxide, and here we're going to make 2 moles of water. So Na is equals to 1 and Nb is equals to 2. So our formula Na over Nb is equals to cover over Cb Vb. So Na, how much is Na? Na is 1, Nb is 2, is equals to concentration of acid is what we are looking for, volume of acid multiplied by time. Okay, so now I'm not going to convert it, I will tell you why. Cb, concentration of the base, is 0.5 multiplied by volume of the base, 20 cubic centimeter. So cubic centimeter will cancel cubic centimeter. Okay, so now you will notice this, that here I have 0.5 is equals to 10 over this. Okay, so here 10 goes once, here it goes twice. Okay, so I have Ca over 0.5 times 2, which is 1. Okay, so I have Ca divided by 1. So concentration of the acid is also 0.5 mole per decimeter cube. Okay guys, so thanks for checking out the video, and part 2 it will be on back titration. Okay, thank you guys, I love you. Please don't forget to like, share and subscribe.